Fine. Yeah. So thank you very much, Dr. Huda. Do you hear me now?
Yes, sir.
Great. It was indeed a pleasure and honor, and thank you for such a nice introduction. I'm really privileged. So I'm going to talk about the tetrapods, which were also discussed in the previous talk by Dr. Goyer. And I will be telling about the basic stuff, how the tetrapods have been started. So the title of the talk is about tetrapod-based smart materials for advanced technology. The image you see at the bottom is our beautiful campus in University of Southern Denmark. And we are the first sustainable development goal university here in Denmark. We are very happy about that. My contact details are here. If you are interested later on, please feel free to get in touch. But where are we located? It is very important to tell. Uh, this is the kind of map of the country, Denmark. Here, this side is Sweden, this side is Germany, and you can imagine Denmark to be kind of several islands connected via the bridge. We are located in the southern Denmark region here, and this also is a little bit related to the name of the university. Actually, University of Southern Denmark was founded by a kind of merging several engineering colleges. There was no university, and then people came up with the idea we should have a university. So all the engineering colleges were combined, and that's how the name comes, University of Southern Denmark. We have a main campus here in Odense, and we have campuses nearly everywhere, starting from this place to, so we are covering the entire region. It's a very new, the university was grounding around 1990, 1998, but we have around 4,000 employees, over 30,000 students. So we have grown up quite fast. We are located here in the Sonderburg campus, the image I have seen in the just on the previous slide, just close to the sea. And here we have our main focus on material science research, electronics and electrical engineering, Center for Industrial Software and Mechatronics. So more or less like a technical engineering side. This city, Sonderburg, also has a history. You might have heard the name company named Danfoss. This Danfoss was originated from this city, and the founder is basically known as the building of the city. Usually, they have donated the campus to us. Actually, they came up with the idea that we should have a university campus here so that we can get the trained manpower. So that means all the industries together around in the Sonderburg area, they decide our programs, and we have one-to-one industry cooperation. Well, that's a little bit about history. So we are exactly working at the bridge between academia and the industry. Our problems are decided by the challenges from the university. We have state-of-art clean room facilities. At Met Institute, we are focusing materials research, and then there are several world-class infrastructures available, and we are open for any kind of collaborations and the research together. Well, the topic of the talk today is three-dimensional nanotechnology motivation. Why do we need three-dimensional nanomaterials? Last 4 to 5 decades nearly, we have been working with nanoscale materials. You all know very well that the most important feature of nanomaterials is their very high surface that comes when their size is very small. In the nanoscale, it is the surface which is mostly dominating and introducing new properties into the material system. We have been working on nanomaterials since long time. We are able to grow them by different methods, physical, chemical, biological, and many other methods. We have understood their properties, physical properties, chemical properties, and many other properties experimentally and theoretically. That is also a kind of now a standard state of art. We have been able to grow the size and understand the properties mainly. So in a kind of a small conclusion, one can say that nanomaterials are more or less well understood, and we understand their properties. We also know, even we are in a state now that we can see atom by atom into the hydrogen, into the transmission electron microscopes. So we have advanced quite a lot. And we also know that where these properties of these nanostructures could be used in certain applications. But then the question comes, despite of 5 decades of research, do we have nanoscale materials? Can we go to the market and buy a product based out of nanoscale materials? There are very few available. There is no straightforward answer. The challenge is that the smaller, very small nanoscale size, which is introducing these nice properties, is also putting a lot of challenges how to use those properties in real applications. So this bridge between the properties to application, now we need to focus at this bridge, how we can translate easily into a product, how we can design the product out of. And mainly there is a challenge. For example, nanoparticles, nanowires, they are very good, but they accelerometer. If we want to make a, for example, a device out of a nanowire, first, we have to make a nanowire somehow by chemical or physical method, and then we have to go to the clean room for the integration. And this integration needs really many complicated steps, and often not successful. It takes quite a lot of time. So we cannot make so many devices in a single day. It is really, really complicated task. So I started my research 12 years ago with zinc oxide and nanowire and the sensing device, and then was really going to the clean room and was feeling the same questions what I'm kind of mentioning today. And then I came out of the box. I was thinking to develop something which is a little bit kind of offering more flexibilities. And while working in the kitchen, I got the concept, got the inspiration from the sponge we used to wash the dishes. And the sponge is built out of a kind of polymer network, some kind of 2D or 1D, whatever we say. And this is a very nice material architecture. I came up with the idea that if I could develop such kind of network out of ceramic materials, say zinc oxide, then I will have access to the surface in a very nice way without going to the clean room. And then I can really kind of utilize, access the nanoscale features in large applications. So that was the motivation. And additionally, you kind of these sponges also giving is a perfect example how architecture can introduce new properties into the material system. Just like if you have a glass rod in your kitchen, if you try to bend it, you will break it. But if you take a glass fiber, you can put it, fold and put in your pocket. The bendability depends upon the aspect ratio. Higher the aspect ratio, more is the bendability. If our hair was 1 centimeter thick, you could not imagine to bend it, but because of very small dimension, we can bend it. So in the same way, one can really squeeze it. You can squeeze such a material. You can expand such a material. You can put something inside to make it multifunctional. You can hold the water. You can capture the liquid. You can release the liquid. So there are many advantages of such a material. And I got motivated to develop this material. Again, the question goes back in the same way. We were talking from nanoscale materials, top-down or bottom-up approach. There are two. You can take a big block of the material and selectively either chemical etching or milling using focused ion beam one can design, but this is not sustainable way because it will take very long time. Another way, one can make the nanowires and try to arrange them into the network form. That is also a difficult process to kind of control everything. There are some good kind of works by Julia from Caltech, but they involve multi-step kind of process into the clean room to design such a network. But I mean, this is really not mass scale, upper scalable process. So I came up with the idea to design these sponge materials by simple process that is tetrapods. That's what our smart materials group is. The tetrapod architecture basically is having a lot of advantages in the sense when you are walking along the water side, uh, beach side, for example, Juhu Beach in Mumbai, you will see a lot of these architectures lying around next to the water. They are there not by mistake, they are there because of certain intention. The advantage is does not matter how you put those ceramic built cement building blocks on the top of each other, they are able to form an architecture which is self-assembled architecture with a random degree of porosity. And this kind of feature allows basically allows to kind of stop to kind of reduce the water drag in a really short distance as compared to the solid concrete wall. In this feature, so I came up with the idea that if we could kind of design these micro and nano scale tetrapods in our laboratory from any material, then I could use this self-assembly feature to construct a three-dimensional network, and that has been successfully demonstrated. So, I developed the process in transport synthesis process, and with that process, I'm able to go the zinc oxide micro and nano scale tetrapods. We call them smart materials. That is our group. And these are some numbers. You can thanks to our colleagues here. This is a recent team. The talk you heard by the comment Goet. He is here with us as a science fellow, and thanks to DST and SCRB for such a grant. We are doing wonderful work. Indra just left 2 days back, so we are very we are focusing our research on the tetrapods. Well, you might be asking the question, how one could build these tetrapods? What is the process? Why gene peptide? So, basically, this process is very simple. What the recipe I developed, we take the precursor material in polyvinyl butyral mixture, fill it into the crystal, put into the oven at high temperature around 900 degrees centigrade. During the process, due to the temperature, the polymer burns. It takes the zinc microparticles up and converts into the atomic vapor, and then with the help of native oxygen, you have a growth from the solid vapor solid growth form of nanostructures. If we are putting a substrate in the top, then one can grow one D layers, different manners. There is a big field I don't want to go. But if you are not putting any substrate in the top, then we have zinc and oxygen clustering, it's natural clustering after hydrogen nuclei is formed, and then we have growth along the four phases leading to formation of zinc oxide micro and nanostructure support. The question is why zinc oxide? And usually it is a community into the community that zinc oxide is almost everything is done. There is nothing left. And I started my research with zinc oxide because there was around 2 million papers available. The beauty of zinc oxide is that it has basically hexagonal modified crystal structure. That means doesn't matter whatever process you follow, you mix zinc acetate with any solution in your kitchen, and we will easily end up with some kind of 1D structures from nanograph to nanoscale, depending on whatever you are following. So that means it offers easy 1D growth because of crystal structure, surface and surface energy minimization. And it was also very motivation that I have been using that time. Uh, and then in this process, the initial lies formed as a metal, and then we have a growth. So sometimes even people will ask, want to work with zinc oxide, but you don't believe on them. I will convince you that there is too much left in the zinc oxide. So I developed this method, the alkaline transformation system method for the growth of zinc oxide micro and nanoscale proposed. This is how the furnace looks like during the growth process. After the growth crucible is filled with white powder, which is mainly micro and nanoscale zinc oxide tetrapods. And here you see basically how these tetrapods form by step on each other with a certain degree of porosity, which is self-controlled, more or less. Just a matter you put them together. This is a loose powder of the and by changing the process into the turn it into the same process, we do have the possibility change the aspect ratio of this kind of homes, because that is the most important thing. We can go from large structures to kind of really like micro scale diameters. Even we can change this length of the tetrapods in a very nice way to high aspect ratio structure here usually. So this these tetrapods we have like happen. The other one they will have like a loose powder and you might assume that these arms, each arms are a kind of quite huge, cylindrical like unical cylinder. But this is not the case. If we go from bottom to top, then we can see that we have a lot of screw-like structures, edge-like structures, steps, no. Basically, kind of a structural arrangement of the surface is going is going to add more surface to the. So in this way, for example, you know that is the advantage of the screw in our game now. And in this way, these tetrapods are very, very good. There is no other materials in these tetrapods. They are completely pure. The same time, they are completely pure, but there are a lot of structural defects in boundaries and structural defects. But these defects are the kind of making them support in a kind of nicer. So the question is how a three-dimensional network of flexible ceramics what set in the vision and the simply very specific concept what was in mind when you go to watch a movie in the theater you buy popcorns. Means the person who takes the popcorn in one scoop and puts it into the box, he doesn't care about how the theater that these popcorns are able to self-assemble themselves to certain degree of porosity. Immediately, you are each popcorn together, take this out, then you find the popcorn network, the same concept I had in mind. And this worked very, very well. What I did to the complex thing is giving an advantage to kind of such porosity, the more kind of complex these arms are quite large. So what we did, we put a mold, we put these tetrapods, the self-assembly feature, the mold was with a well-defined formula, and then now we decided to control the density, and in this way, basically we have kind of construct architecture inside of how to do each set of together. One can apply chemicals, one can apply several things. But I was using the hard way to do to set high temperature of 1100 centigrade for 5 hours. And this allows the formation of these three-dimensional networks in a very nice way. It's how any shape or any size in a very good way. One type of such networks is that in the all these networks are having density at around 2.3 gram per cc, that means the price is around 94%. They are highly motivated and dense molecules like rubber lighting molecules, they are insulated, they are stable, lightweight, highly porous, and also flexible. So usually the main difficulties to grow these type of boats and to grow these three-dimensional interconnected network out of engineer their numbers and make them multifunctional in several ways. I think the normal features in the large dimensions. So this has been pushed up our research. I will show some of the application examples. And this is a study and the scientists and the engineer and zinc oxide is insights in the industrial design and therefore everyone who ever want to work with zinc oxide, if you go and ask them on that application, the first idea was, yeah, I'm making sense actually. And when you make it out of the nanoscale element, you have a nano element, and it's not how you integrate it into your device. It's a matter of fact, which you kind of sensing, optical sensing, incident sensing, and dielectric sensing, plasmonic sensing, optical, whatever electrical. Here I'm talking about electrical sensing. And sense of sensing have a nano element, something is and comes our nano element, and every element is changing its feature, either electrical or optical, whatever feature, and that is measured the change in the response of the nano element. And here, again, very nice idea to use this kind of element from the sensing element to get out of a lot of advantages. It's very easy to make as compared to simple in the nanowire. It has a high precision.
Sorry to interrupt you, Dr. Yogen. Please fix your mic because you are not audible clearly.
Can you hear now?
Yes, sir.
I don't know why it goes like this. Hmm. Yeah, can you hear now?
Yes, sir.
Yeah, now it is better. Earlier it was having too much of disturbance. Now it is better.
Oh, yeah, thank you for disturbing. Yeah, so basically we decided to use kind of these flexible elements as a sensor, and we have demonstrated UV sensing and the gas sensing very nice way. We have understood the properties, kind of sensing response as the increase or decrease into width of the conduction channel. We have even made those hybrids. So as the community moves, UV sensing, then gas sensing, and then going to environmental and biological sensing, more or less. Now biological sensing is very, very important, after the corona time. This is coming as a kind of good interface, and the good advantage with such network is that even the large objects can move inside, and they can be kind of, because the structure size is large, they can contribute to the sensing. They can be easily captured and sense. So there are many properties. These networks are bendable. If we have a bendable substrate, they are high temperature stable. So high temperature sensitivity is also important sometimes. And they are zinc oxide material has a non-centrosymmetric hexagonal woodside crystal structure. That means if you bend it, then you are developing a piezo potential. So it can be used also to self-power the devices, more or less self-powered sensor. So we have done quite a lot of research in last 10 years, but still we have the challenges like selectivity we have to address. I mean, in the lab everything works perfectly, but if I take the kind of my sensor to the airport, and if it can tell which gas it is sensing, then it makes sense. Zinc oxide is physically very kind of robust material, but chemically it is kind of not stable into the acidic environment. So one has to think about, and there are several other compatibilities we are trying to understand in collaboration. We have published quite a lot, but still yet to deliver a product into the market. And very recently, we are trying to integrate both kind of for for pollutant monitoring, degradation, and sensing, both aspects together in collaboration with Korea. So that one research is going on. That is one aspect of application. The second aspect of application is polymer engineering. You have heard in the last talk by Dr. Goyat that more or less you are putting nanoscale materials in every type of polymer material to improve its properties: mechanical, electrical, optical, dielectric, thickening against resistance or whatever something. And when we put nanoscale materials into kind of polymer, we are always caring about kind of agglomeration, because agglomeration is a big problem. You do not want to have them, but it always kind of happens. And the place where agglomeration takes place into the polymer, that is kind of a defect into the composite material, because there the symmetry is broken, the periodicity is broken. So in fact, these tetrapods have been very good filler materials, because doesn't matter how we place them together, they are very easy kind of, they are dispersing themselves into homogeneous manner, and that is really giving lot of advantages. So this is one separate field of research we have been working on. We have demonstrated improvement in mechanical, electrical, optical, dielectric, and wettability, many other properties of the polymer. If I focus on this aspect, this could be an independent talk. I could talk weeks about what we have done, and we have been very successful. Some tetrapod base coatings have already been applied to the windmill kind of wings already as a stable coating. Yeah, just as an example, not only as an excellent filler material, we could also use them as a excellent support elements. Often we want to disperse, for example, any chemical molecule into a composite material, polymer, but it is very difficult to homogeneously disperse, for example, spiropyran molecule, which undergoes color change to design, say, a kind of self-reporting material. If you make any damage, if there's a material, if there is a damage on the surface of a composite, you can easily identify. But if there's a damage inside the composite material, for example, then you have to kind of really damage the material to identify damage. So these markers could be a way to identify any damage beforehand to avoid the catastrophe. So the spiropyran molecule, it was difficult to disperse inside, but we loaded these molecules on the top of the tetrapods, and then we used them as a kind of this whole body as a filler material to uniformly disperse them into the PTU matrix. And this matrix was showing a color change under the impact of heat, light, and the force. So we have been in this business in composite engineering and designing really lot of self-reporting composites, advanced composite materials, joining the two polymers and defouling composites would be. If you are interested, then please feel free to get in touch. Recently, we have used these tetrapods even to engineer the wax properties as a kind of thermal engineering to harvest the solar energy into kind of renewable energy, more or less by latent heat interplay, by from solid to liquid, liquid to solid, something. So there is a lot of scope of these tetrapods into composite engineering materials. I will not take too much time, and I will go to the next topic where we have high application scope. You know, with any new materials, there is always kind of open question. Okay, can we have any application in biomedical engineering? Always, like a normal researcher, everyone is asking. I was asking the same, and I met with a colleague from University of Illinois at Chicago who was virologist, and he said, Yogendra, why don't you send some tetrapods? Maybe we can find something interesting and publish a paper. I was sending the tetrapods, and then after 6 months, he came up with a very nice result. Yogendra, these tetrapods are blocking the virus. They have the capability to bind the viruses. The viruses, when the virus come in touch, close vicinity to the tetrapods, they are getting bound on the surface. And we are talking about viruses, this herpes simplex virus 1, which comes on our face, usually on the lips, and it goes over time. These are enveloped. The virus envelope is made out of heparan sulfate, and normally they go to the cell, they interact with the cell surface, with the receptors, they enter into the cell and then damage the cell. But if we have some nanostructures, zinc oxide, tetrapods, CHN, then they are bound to the surface of nanostructure, so the viral entry goes down. And then later on, we demonstrated that after binding, they are getting destroyed, also neutralized as well. So the mechanism was very simple. Zinc oxide has a positively charged surface, and these viruses are having negatively charged surface, so they are kind of having some kind of attraction Plus the scale, length scale matters. This staircase structure helps a lot. I can talk more if there is a time remaining later on in the question session. So we demonstrated that if you illuminate the UV light, then the viral binding goes up because the positive surface goes more, and this worked quite nicely. And then we published the paper afterwards. We got quite motivated, and we have done now the study with these tetrapods against 10 types of viruses: herpes simplex virus type 1, type 2, zoster, genital murine, monkey virus, human papilloma virus. So we're quite a lot. We have been very, very successful. One question we all should ask when we are working with nanomaterials and motivated for healthcare, that what about the cytotoxicity? And luckily, these nanoscale, these tetrapods, due to their three-dimensional size, large size, they have less cytotoxicity as compared to the nanoparticles because they cannot penetrate into the cell membrane easily. And that gave us a really a very nice advantage. And to keep the story start here, just we infected mice with genital herpes virus, and then we treated mice, and here is the result that these mice survived really, really long as compared to the control animals. Here we have demonstrated the binding. This is the genital herpes virus, tetrapods, and usually these tetrapods have three functions. They are able to bind the virus, they are able to trigger the cell signal due to the immune response, and there is certain release of zinc ion which is promoting the cell growth, so the wound healing is much, much faster. So this has been United States patent actually. And we at previous place in Kiel, we had a company Firestone AG that has opened that is now upscaling. That has upscaled already the data for growth process, and they have demonstrated a kind of, we did human studies and animal studies with positive results. There is already a product available into the market of Novia, that is the cream. So people are eating usually these kind of clear as a medicine, but with this cream one has to just apply where the viral infection is, and this is gone. So we have a history since 10 years. The replication, the multiplication has not been taken place. And zinc is a very important element for human body. Unfortunately, the zinc oxide, that if you talk with the doctor, he has a different perception. If you talk with a tire company, they have a different perception. If you talk with a chemist, if you talk with a biologist, material scientist, physicist, each is carrying a different kind of opinion. But now the situation has come. At least I'm trying to that we also talk together that we should not. There's a high kind of a score for zinc oxide biomedical application. Zinc controls nearly 200 metabolic functions in our body, and if zinc oxide goes in our body, it can be decomposed into the acidic medium. So this is a very important biomedical material. If you didn't know, you know after during the corona time that people were eating zinc supplements, tablets, just to boost the immune power. So this is such an important element into the body. If I focus on biomedical aspect, I can again talk for hours, weeks, and months. So, but and actually, we were very successful in nearly every direction. We tried to conduct our. I would like to here introduce you to a new concept that if this test report, if the safe is still successful, can we, as a normal researcher, we ask that grow that report from every material into the periodic table? And the answer is no. It is not us who decide how material should grow. It is the material deciding how it wants to grow. But this chemical instability was really an accident, but that it told us a lot. It gave us a new direction of research, 3D materials engineering. The idea is that we could deposit something on the top by any method. Yeah, and then we could remove easily on the backbone. So we have been using this
Sir, your
proposed.
sir, your
Yeah,
mic is sir, your mic. Please adjust it again, sir.
I don't know why did it happen. There's something happening with your side. Can you hear now?
Yes, sir. It's good.
I don't know why did it happen in between. Mm, Sorry. So basically, kind of, we came up with the idea that we could deposit something on the top, and then we can remove the underneath backbone. And this has been really very successful. We started a new field of research of 3D materials engineering. This is the carbon nanotube solution which was dropped on these tablets. You can see that the kind of CNTs are wetting very uniformly the entire network. Now it is a composite material. Nearly everything, whatever you wish to add on the top of this tetrapod network, you can add. And that means you have two functionalities now into the composite form, zinc oxide and carbon nanotubes. And if one requires as a composite, one can use as a composite. But if one requires basically a new material, then by chemistry we could remove the underneath backbone, and then we could really kind of get a new material exactly into the same template form, 3D network form, with high degree of porosity, sponge-like material. And this has been our state of art in last 5-10 years. Almost we can create every kind of new 3D materials by the same process, using them, these networks as a template. You can see this is a PDMS network, the degree of porosity and everything, whatever you can prepare. So this is the kind of typical carbon nanotubes tube network we can made this story. And here you see that after adding CNT into zinc oxide, they wrap around, and then after removing basically zinc oxide, we have a carbon nanotubes tube network. These carbon nanotubes wrap around the arms of tetrapods like kind of the bamboo lacing we make in our daily life, and then they provide huge mechanical strength depending upon the carbon nanotubes content. And then afterwards, when we have enough content, whole coverage, then we remove, and we have really a nice mechanical strength. We have very high porosity, several order of porosity, and then we have nice electrical conductivity. And these networks have shown many applications as a high sulfur loading cathodes into the battery materials or medical catheters. So that we have demonstrated. Even not just carbon nanotubes are the solution, we could grow even the kind of large, very tough materials like boron nitride. It is very difficult to grow boron nitride in simple conditions into the 3D network form, but using these templates into the CVD process in simple VLS chamber with the help of ammonia and borax chemicals, we really deposited boron nitride and removed the underneath zinc oxide, and such a boron nitride network was created. And we demonstrated this boron nitride network hexagonal as a light diffuser element. You know, in the early days, 90s, 2000, when we did in the bachelor experiment in the lab, we were most of the time we were struggling to get a monochromatic wavelength out of this very fine slit, usually kind of to do our optics experiment. Now we are living in LED era, and LED, why? Because LEDs give really nice light with kind of low power requirements, so they are much better. But LEDs do have the kind of problem of efficiency drop at high temperatures. So we are talking about now exactly opposite to what 50 years ago, how to convert a coherent light. If we can use a laser light to design a white light, then we need much less power and better quality of light. I mean, now we are talking about how to convert a coherent light into a diffused light, exactly opposite to 50 years ago, for 30 years ago, more or less. And their standard RGB elements cannot work because they cannot sustain with the laser power. So we need new diffusing elements, and these diffuser elements could solve the kind of challenge. And here in these, they work as a perfect diffuser. We have demonstrated the conversion of laser light into a nice, very nice white light. And the advantage is if you apply a mechanical stress, you can change the scattering pattern, because you have all possible quantum mechanical path lengths close to the wavelength of light, and you have a lot of constructive and destructive interference. So you can generate a very nice speckle pattern. And we have been really making kind of graphene seeds, converting into the three-dimensional network form to use them in many applications like medical catheters and everywhere. So this has been a new field of research. What we have started from this, converting every material into a three-dimensional form, into including gallium nitride, hard ones, and the boron nitride, and then using them for particular applications. So we are moving away from substrate requirements. There is no substrate needed. You have a sponge-like materials you directly harvest. So if there's any interest, you are interested in any new three-dimensional material, we can take a challenge. Yeah, and even a very complex form of network, we could prepare AU nanowires wrapped into the hollow silica network. So hollow silica nanotube network was prepared using the same approach, and then gold nanowires were wrapped. So this was a very nice plasmonic composite, basically 3D composite. So we have developed. One other application aspect is basically application of nanomaterials into the water. You know, in our laboratory, we use nanomaterials for photocatalytic decomposition of dyes, water purification. We write nice papers and report nice performance. What we are not talking about, that if we are contaminating water further with our nanomaterials. Today it is not a problem, but it could be a problem in future. I'm quite sure after 20 years we will be talking about nanoparticle pollution in our environment, like microplastics. Today in 1960s the plastics was not today. The advantage with such net materials is that in general with nanoparticles you have no possibility to kind of analyze the post effect on the nanomaterial, what has happened. But here this is a structurally intact material, so you can analyze the material after the effect has been taken place. So we know the material history a little bit more, and in this way they are good backbone. So in fact we have demonstrated by Dr. Joshi, Monica Joshi from Amity University. She was coating these tetrapods with activated carbon, and then kind of this was showing a nice decomposition of chromium 6 into the chromium 3, and this, she was also coating them with magnetic nanorods, iron oxide, encapsulating, and very nicely as separation of diesel from water was demonstrated. So the good thing about it, that we could put any nanoparticle on the top, we can nicely localize it, we can have access to the surface, and both to the zinc oxide and to any nanostructures. And then this is kind of backbone is controllable. We can easily analyze afterwards the effect. So they are perfect system for water related, liquid related applications. Recently, we are jumping into the piezoelectric response into the 3D network materials. Experimentally, we have demonstrated that if we bend the tetrapods, then how the piezo potential is going to be created. But this is up to the theoretical level. Experimentally, we are trying to demonstrate. So it will come up as a nice study. And but I'm mainly a materials engineer, and I keep kind of my focus always to create new materials. That's where, so in collaboration with MIT, we started working together. If we can put these tetrapods into the fibers, electrospinning. Initially, they hesitated, so they were breaking the tetrapods, and when they were putting into the fibers, what happened? These fibers were used as a membrane to treat at the root canal, and they nicely demonstrated with 2% of zinc oxide the separation of bacterial growth at the root canal. And this allows them, basically they got motivated, and then we put the tetrapods, and we were able to design these rose spike like structures. These spikes are zinc oxide spikes, and this is a PCL fiber. We demonstrated this. PCL is a polymer fiber, biodegradable fiber, which is used to stick the wounds. We always have a question of reinfection after the surgery. and by adding some percentage of nanostructures, we could make it sure that there is no reinfection. In general case, we are scaring about if nanoparticles could move to the wool, but here these tetrapods are nicely locked. They are not going to go in. They are delivering the effect, so they could be really good integration to the biomedical direction. And recently, we also demonstrated that they are able to block the viral entry into the thing. They can find the viruses and then they can really neutralize the viruses. That opened us a new direction of research. We have now electrospinning facility with us, and we can definitely integrate these tetrapods in a very nice way design. And we are working on designing smart materials for banded application, textiles, and many other. So this is a new direction of application we are focusing on. I don't know how much time I have left, but I am at the end of my talk. So as I mentioned in the beginning, people were asking me, if the community was saying when I started my research with zinc oxide that okay, there is nothing left in the zinc oxide, everything is known, has been understood. But after working 12 years, 13 years with zinc oxide, I'm at the conclusion that there's a plenty of scope at the bottom in the zinc oxide. If you combine the shape and the functions and the structural engineering and with multi-functionalities, then there is too much to do to learn about the side, particularly with respect to the real application. These materials, they have the capability to bridge the gap from lab to life. Many applications, our email have been there kind of to work on functional 3D surfaces, new chemistry, new materials, new properties, and new applications. These are some cover images what we have been. So with this, I would like to thank my collaborators and the funding team worldwide. I cannot list all the names, so if you find there are some names missing, can happen. But I really thank all the collaborators who have been helping us. We are mainly interested in materials engineering, thanks to Rainer and Otherland at Kiel University, funding agencies in Germany and funding agencies in Denmark, plus all the colleagues who are helping us. And mainly, I would like to re-advertise a little bit here from the work in such a way that we know we have a lot of industries around and they are looking for always the new challenges, kind of they are coming up with the new material challenges, and based on that, recently we have launched a new program and it's in physics and technology engineering, where the deadline is open 1st of January until 1st of February, and
Sir,
those
please fix your mic again, sir.
is I never encountered before. Sorry. Is it okay?
Yes, sir.
Sorry, I never encountered this before. So we have this new program and we are looking for very
Okay, now.
bright, we are very bright, motivated candidates. So if you are talking any young students, I know you are telling US, Australia, Germany, UK, but if you find a good motivated candidate who is willing to do masters, please consider Denmark and also Sonderberg to our program as well. Just BSc students are also welcome if they have such curriculum. So please go through in the detail and we will be happy to answer any question. The good thing about it that we do have job guarantee after the course. So if students are coming, they will get the first job in the after successfully completing this master's course. And you know the beauty of job in Denmark, it's one of the best paid job one can ever imagine something. So please, that is an advertisement. I request you to tell the colleagues. I'm also running a program with Smart Materials for Advanced Technologies. So if you find any bright, motivated young candidate, bachelor's or master, who is willing to do the thesis or internship for 3 to 6 months, I will be happy to entertain. So with this, I would like to say thank you very much, Dr. Huda. and the entire team for inviting us. The last announcement, I'm also organizing European MRS in Strasbourg. So if you are willing to come to Strasbourg in this MRS conference, please kind of submit your abstract. I will be sharing the informations later on. So with this, I hope I have been able to introduce some informations about tetrapods and some other scopes. Thank you very much again, Dr. Huda and the entire team for having me on board as a keynote speaker. And I'm looking forward for the questions and interaction session.